Hi, everyone. We're up to section 6.5, the binomial probability distribution, and this is the last section in chapter 6. So the binomial probability distribution is a specific type of discrete probability distribution. So in the previous lectures, we've covered discrete probability distribution. So we're still going to be working with a discrete probability distribution, specifically a binomial probability distribution. And I'll get into the definition in a little bit in terms of what a binomial probability distribution is. But I think the nicest way to introduce this concept is to first do an example that you guys could do without even knowing that this is an example of a binomial probability. And then I'll make the connection. So let's look at example 8. A fair coin is tossed 2 times. Calculate the probability of A getting 2 tails and then B getting at most 1 tail. So first, let's think about how many outcomes are there in the sample space. So remember at the beginning of chapter 6, I bundled chapter 5. So the first page of this handout was just a quick review on probability of equally likely outcomes when we have an experiment that has equally likely outcomes. Well, this is an example of an experiment that has equally likely outcomes, and we could easily figure out these two probabilities. So just a quick reminder, the probability of an event E is equal to the number of outcomes that satisfy E divided by the total number of outcomes. And we practice this in the chapter 5 lesson. So we're going to toss a coin 2 times. So let's think about, before we even get into the probability questions here, let's think about how many outcomes there are and what they look like. So imagine you have a coin in front of you and you're going to toss it twice and write down what you get. So for example, you can toss it 2 times and heads could appear both times, right? So one possibility is head, head, right? It's possibility to get a head and then another head. So this would be one possible outcome if we tossed a fair coin 2 times. Think about another possible outcome. What about tail, tail? It's possible that we flip a tail and then we flip again and we get another tail. But these aren't the only 2 possibilities, right? We can get a head and then a tail. That's a possibility. Or a tail first and then a head. But that's really the only 4 possibilities because we're only tossing this coin 2 times. So there's 4 possible outcomes. That's it. So in part A, I want to know what's the probability of getting 2 tails. So we can use our probability, our classical probability definition. So we're going to divide the number of outcomes that satisfy event E by the total number of outcomes. So let's set up our fraction. I think it's easy to identify the denominator first because the denominator is the total number of outcomes, which in this case is 4. So my denominator is going to be 4. And then out of the 4 possibilities, how many satisfy the event of getting 2 tails? Just one, right? There's only one outcome that has 2 tails, the TT. So the numerator is going to be 1. So my answer is 1 out of 4, or 0.25, if I want to write it in decimal form. So there's a 25% chance that if we're going to toss a coin twice, we're going to get 2 tails. So now let's look at part B. Part B says, what's the probability of getting at most 1 tail? Now, at most means that's the most amount of tails we could get, but we could get anything less than 1 tail. So this includes the probability of 1 tail we don't have to write this down. We can kind of just say it out loud. The probability of one tail or zero tails, right? That would be at most one tail. We could either have the most one or none. So let's look at our possibilities. And no tail, let's start with how can we get no tails? Well, no tails would be head, right? So we could get either zero or at most one tail. So which outcomes have one tail only? These two, right? Head, tail, tail, head. We're not going to include tail, tail because that includes two tails, which doesn't fall, within the event at most one tail. So this is going to be 3 possible outcomes out of 4 total outcomes, right? There's 4 outcomes altogether and 3 have at most one tail. And if we simplify that, my probability is going to be 0.75. So there's about a 75% chance that if we were to flip a coin 2 times, we're going to get at most one tail. Basic probability. But this experiment is actually going to be considered a binomial experiment. So I use this as an example because this is something that we were easily able to calculate, right? But we could also look at this from a different perspective. So the previous question that we just did, like I said, is an example of a binomial experiment. Think 2. We can classify the outcomes of a binomial experiment into two categories, a success and a failure. In the previous example, getting tails would be considered a success and getting heads would be considered a failure. So whenever we speak of a binomial experiment, you have to always think that there's 2 categories, 2 possible outcomes, either success and a failure. A success, though, doesn't necessarily have to be something good, and a failure doesn't necessarily have to be something bad. That's just what we call it. Think of the success as the characteristic that we're interested in, right? Like up here, we were interested in getting tails. We were focused on A and getting 2 tails, B getting 1 tail. So getting a tail is being considered a success. Anything else would be a failure. And what's the only option? Heads. So that's why we would consider heads a failure. So there's 4 criteria to a binomial experiment. There has to be 4 conditions that are satisfied. The first one is that there's n identical trials. Just think of a trial as a stage. So for example, how many stages were there to this experiment when we tossed the coin 2 times? Since we were doing it 2 times, there was 2 trials, toss 1, toss 2. So just think about how many stages are there to the experiment, and they're identical, meaning we perform them the same way. So there has to be n identical trials. And then that specifically the n identical trials have to be independent. And what I mean by that is that the outcome of one trial is not going to be affected by the outcome of another trial. So for example, when we flip a coin 2 times, the outcome on the second flip does not depend at all on the outcome of the first flip. It's an independent trial. There's no dependency there. The third characteristic or third condition is that the outcome of each trial be classified as either a success or a failure, which we just talked about. And the fourth condition is that the probability of a success is the same for each trial. So if we go back to this example, so we were considering a success getting a tail, right? Now, there were 2 trials here, or 2 tosses of a coin. Every time we toss the coin, you have the same probability of getting a tail. It's always 1/2, right? When you flip a coin, you have a 1/2 chance or a probability of 1/2 that you're going to get a tail. And that doesn't change. From trial to trial, it stays the same. So that's why this example that we just did is an example of a binomial experiment. It satisfies the 4 conditions. Now, rather than doing it like we did here, where I listed all the possible outcomes of my experiment, and then we formulated these classical probabilities, we could use what's called the binomial formula, and we're going to get the same answer, and it's going to be more efficient. This wasn't so bad to list them all because there was only 4. But what if we tossed the coin 80 times? There would be way too many outcomes to list. So we wouldn't be able to do this by hand just by looking at the sample space. So we have a binomial formula that's going to help us solve these binomial probabilities. So it's called the binomial probability formula. So for a binomial experiment, the probability of getting S successes in N trials is computed using the binomial formula. And we can write the formula as follows. So we say the probability of success, or S successes in N trials, is equal to, let me make this a little bigger. So we say this first set of notation is called N choose S. So N, that C stands for choose, and then S. This is called a combination in math. So what it tells us is how many different ways we can choose S items from N items without replacement and without order. So basically, this N choose S is going to calculate how many different ways we can get S successes in N trials. So for example, if I want to get 2 tails or 2 successes when I toss the coin 2 times, that N choose S is going to tell us how many different ways we can do that. It's the possible combinations. Then we multiply that by P raised to the S power, where P stands for the probability, and I have everything written down here, where P stands for the probability of a success for one trial. And we raise that to the number of successes that we're interested in computing. And then we have to multiply that by Q, where Q represents the probability of failure, or 1 minus P, because a probability of a success plus a probability of a failure should equal 1. And then we raise Q to the N minus S power. So the number of trials minus S successes. And that's how the binomial formula works. And we'll use the binomial formula to rework example 8 that we just did by hand. So let's rework example 8, but this time we're going to use the binomial formula, and I'll show you guys how to use the formula. So this is example 9. And remember, in example 8, we were tossing a coin twice. And in A, we wanted to know the probability of getting 2 tails. So before we plug into the formula, we have to know what N, P, Q, and S are. So N stands for the number of independent trials. So in other words, how many times are we tossing the coin? So in this case, N is equal to 2 because we're tossing the coin twice. Now, a success is, what are we considering? What do we want to try to calculate here? In this case, it's the probability of 2 tails. The characteristic is being a tail. So we're going to consider getting a tail a success. So that's going to be the number of tails that appear. Particularly in part A, S is going to be 2 because we want 2 tails to appear. So for part A, we have N is equal to 2. S is going to be also equal to 2. And then we have to figure out P and Q, where P stands for the probability of a success. And we're considering a success getting a tail, right? For any one trial, if you were to toss a coin once, what would be the probability of getting a tail? And that's 1/2 or 0.5, right? So P is equal to 0.5. And then Q is the probability of a failure, and that's just equal to 1 minus P. So Q is equal to probability of failure, which in this case is getting anything but a tail, which is getting a head, and that's equal to 1 minus p. So Q in this case is 1 minus 0.5, which is 0.5. So P and Q happen to be the same in this case, since when you toss a coin, you have a 50-50 chance of getting either heads or tails, right? So now we're ready to plug into our formula. So the binomial formula is n choose s times p to the s power times q to the n minus s power. So in this case, we want the probability of 2 successes, right? Because we want 2 tails. And here are my parameters that we're going to plug into the formula. So P of 2 is going to be equal to n choose s, and I'm going to show you how to find n choose s in a minute. So n is 2, so we're going to have 2 choose s, which in this case is 2. We're going to multiply that by p, which is 0.5. So we're going to multiply that by 0.5 raised to the s power, which in this case is 2, times q, and I don't really need that caret there, times q, which is 0.5, and we have to raise that to the n minus s, where n is 2 and s is 2. So 2 minus 2, which is equal to 0. Now, a couple things before we plug this into the calculator. Let me show you how to find a combination, and I want to talk about the 0 power rule, just as a reminder. So I'm going to go to the whiteboard for a minute. So first thing real quick is anything to the 0 power is equal to 1. So a to the 0 equals 1. So for example, if I have 10 to the 0 power, that's equal to 1. If I have 4 to the 0 power, that's equal to 1. If I have -6 to the 0 power, that's equal to 1. So anytime we're going to raise something to the 0 power, the result is equal to 1. And then now let me talk about how we calculate a combination. So n choose s. So for example, if I want to do, so let's do the one that we're doing for this example is 2 choose 2. So if I want to do 2 choose 2 in the calculator, first, so in the calculator, first we're going to press 2. Then we're going to press math. And we have to pull up the combination function. So we're going to arrow over to PRB, which is probability. And then we're going to choose the combination option, which is option 3. And in the calculator uses N choose R instead of S. That's just what the calculator uses. Then we're going to type in the other two, right? Because we're doing 2 choose 2. So whatever S is, we have to type that in and then enter. So let me show you how to do this on the calculator. So first I'm going to press 2. Now I need the choose function. So that's when we press math. We go over to PRB for probability. And you see option 3, the third one down, is your combination and choose R. But again, we're using S instead of R for our formula, but it's the same thing. So it's going to pop up as NCR. Now you have to type in S, how many successes we want, which is 2 in this case. So 2 choose 2, and we get 1. So there's one outcome. So 2 choose 2 is equal to 1. So 2 choose 2 is equal to 1. And now we have to multiply 0.5 squared, right? So we're going to take 0.5 squared. So take 0.5 and you're going to square it. And we get 0.25. And here we have 0.5 to the 2 minus 2, which is 0, right? And anything to the 0 power is 1. So that's really 1 times 0.25 times 1, which is 0.25. So the probability of getting 2 tails is 0.25. And that's the same exact answer that we got when we did it by drawing out the 4 possible outcomes, right? The probability of 2 tails was 1/4 or 0.25. So whenever you're working with a binomial experiment, if you use your binomial formula, you're going to get the same answer. And we already have this binomial formula programmed into the calculator. And in the next video, I'm going to show you how to use the function in the calculator so you don't even have to write this formula out. We can make our life even easier by telling the calculator, you know what? Use the binomial formula. Here's n, here's p, here's s. Go do it for me. But I like to show you how to use the formula by hand first because I think that's important. So it's not, a mystery or magical where the calculator's coming up with these answers. So before we wrap up, let's just do part B. So part B was the probability of at most 1 tail. So at most 1 tail includes the probability of 0 or 1 tails, right? Because at most 1 means it could be 1 or anything less. So it's possible that we get no tails or 1 tail. So we have to add these two probabilities together. So we're going to have to do the formula twice. So first we're going to have to do the formula for 0 tails. Then we have to add and do the probability. So we're going to use the formula again for the probability of 1 tail. So first, we're going to look at 0 successes, right? So P of 0, when we're talking about a binomial experiment, this is 0 successes. So in this case, S is equal to 0. So you know what? Up here, let's write this. So let's do the probability that this is the same thing as the probability that the number of successes is equal to 0 plus the probability that S is equal to 1. So let's plug in the formula for when S is equal to 0. So we're going to have N choose S. So N is still equal to 2. The number of trials doesn't change. So we're going to have 2 choose now S, the number of successes, which is 0 in this case. So 2 choose 0. Times P to the S. So all I'm doing is following my binomial formula. So P is still the same. It's 0.5 to the S, which is 0 in this case, right? Times Q, which is 0.5 to the N minus S. So the 2 minus 0, which is 2. And you'll notice the 2 exponents should always add up to N, the number of trials. Plus, now we have to do this again for 1 success. So 2, so n choose s is going to be 2 choose now 1 success. And then we're going to have 0.5 raised to the s, which is 1 in this case, times q raised to the n minus s. So to the n, which is 2, minus the number of successes, which is 1, and that's going to give us 1. So we need to plug into the formula, the binomial formula, 2 times in this case. But we know we should get 0.75 when we do this, right? Because when we did this by hand up here, the probability of at most one tail was equal to 0.75. So let's plug this into the calculator. So let me show you how you can plug this into the calculator all at once. We don't have to do it in separate pieces. Just make sure you have parentheses around each part of the multiplication. That's it. So let's go to the calculator. We'll do this together. So open your parenthesis. First, we're going to do 2, choose 0. So I'm going to type in 2. Then I have to choose my combination, right? So math over to probability, and it's option 3. So 2, choose 0. Close the parentheses. Now I'm going to take 0.5, and I'm raising that to the 0. Close your parentheses. Now open, and we have to do 0.5 raised to the 2 minus 0, which is 2. Close your parenthesis. So that's the first part of the binomial formula for 0 successes. Now we have to add that to the probability of 1 success. So plus, now open a parenthesis, we need to do our combination again, right? We're going to do 2 and then choose 1, close the parenthesis. Now open, and we're going to do 0.5 and, 0.5 raised to the 1. Now we could close the parenthesis, times 0.5 raised to the 2 minus 1, which is 1. Close the parenthesis. And we already said we know we should get 0.75, right? Because we did it by hand. And we do, right? We get 0.75. Now, I know this seems like a lot more work than the way we did it by hand when we listed the 4 outcomes and we used the classical probability formula. But there was only 4 outcomes. Like I said before, what if you had 500 outcomes? There's no way you're listing them all by hand and counting up all those, probabilities. It's not happening. So whenever we have a binomial experiment, we're going to be much better off using the binomial formula. And this is how you use the formula by hand. And in the next lesson, I'm going to show you how to use the formula that's already programmed into the calculator. We do have a function in the calculator to calculate binomial probabilities. So we'll do that next. So let's just write down this answer, 0.75. And in the next lesson, I'm going to show you how to use the calculator to pull up a binomial function.